Good afternoon, everyone. I am Anubhi Khandelwal. I am the digitalized automation specialist for Siemens Digital Industries based here in UK in Manchester. I provide pre-sales and post-sales technical support around Siemens virtual commissioning portfolio within UK. So today we will have a look at creating the digital twin of your machine, just the mechanical side of it. So like James said, on Monday we did on the bit on automation side, on Tuesday the peripheral simulation of electrical bits, and today is the machine. So we will start with the overview of NXMCD. What does it look like, its basic features, followed by how to create some joins, some sensors, basic material flow, which will then be followed by creating some inverse kinematics for robot handling, and then finally creating some CAM profiles within NXMCD using some position controls and how it can then be imported in TIA portal later on. I will do a quick screencast at the end just to bring MCD with automation side, so your controller together, but the complete end-to-end virtual commissioning, we will be doing it tomorrow with 3 different software coming together and creating a complete digital twin. So let me show you my NXMCD, and this is how NX looks like. So right now it just says NX because NX is our CAD offering. MCD or Mechatronics Concept Designer is an add-on to NX. I can create a new file, so I can go new. I can choose whether I just want to do some modeling or I want to go straight in Mechatronics Concept Designer, and I can choose some basic setup. So I can say general setup and okay. So when I do that, it just quickly creates a file, a project for me with nothing, just a rectangle here, which is called floor. And we can see now we are now in Mechatronics Concept Designer. Okay, so how it looks like now, we can see that this is our graphic interface where we actually see the machine, how it sits in the 3D world. But once we start giving some kinematics, and when I say giving some kinematics, I mean we give it some mass, some friction, it falls under gravity, it behaves, it interacts with other bodies around it. So basically making it look like an actual machine. Once we start creating it, giving it some kinematics, you would start seeing them appear here. So some basic physics, joints and constraints, what sort of material we are using, all that sort of stuff. And this is called Physics Navigator. Then we have something called Runtime Inspector. A Runtime Inspector basically allows you to see the runtime values during simulation. So if it's a speed controller, we can see what's the runtime speed or the runtime position of any object. We have something called Runtime Expressions. So we can write some expression that runs in the background during simulation, some basic formula like if A, then B, or something like that. Then we have the Assembly Navigator. Assembly Navigator gives us the complete part and the hierarchy of how each part sits under what assembly. And then we have some reuse libraries as well. So once you start creating some physics here, if you want to save your project, if you want to reuse your components with all the physics included, we can use them in the reuse library. I am not going to model anything today because this is more about how to use MCD and create a twin of the machine, not how to model it. So we will just be looking at that. Okay, so let me close that and I will. Okay, so we will be working on this basic machine here. We've got 2 conveyors. We've got a box that will be going down the conveyor. And we've got a few sensors here. Right now, if I play, nothing happens because while in the CAD world, we can see something that exists. In MCD world, there is no physics or no kinematics attached to it. So that's why nothing happens and you don't see anything here. On top, we can see loads of buttons that can help us create our MCD model. So if I start with something called rigid body, as I said earlier, we would be creating some rigid bodies. I can just select it. I can select the mass. So it could be automatic or user-defined. When I make it user-defined, I can specify the center of mass or the center of coordinate system, inertia, and all of that. I will keep it automatic for now. And I can give it any sensible name which is recommended to do. So I say, okay, when I give it some mass and it's a rigid body, we would expect it to fall under gravity because there's nothing else holding it there. So to do that, we can create some collision bodies. So I can create a collision body. I can call it collision body 1. I can create another collision body. And I should also create a collision body for my box itself because box is what's going to collide with something else. Now you can see we have different shapes here for collision bodies. So you can have a box or a sphere or a cylinder. It depends what sort of object you have there. So we will keep it a box for now. And I say, okay. So very quickly, we've created a collision body, a few collision bodies and a rigid body. Now when I play, it goes and sits there, as you can see. And I can move it around, drag and drop it. And because now it's left the surface, it's probably going to fall down. Right. So that's just the basic stuff. The next thing that we want to see is see our boxes moving down the conveyor. So to do that, I have something called transport surface. So let's have a look at the transport surface. We can select the face. We can select the direction. So when I select this, it means this is the positive movement. This is the positive direction. And I can specify some velocity. Now this could be hard-coded in here, so I can just say run at this all the time. But whenever I connect it to my controller or sim it, I can override this value. So when it's a drive that's controlling my conveyor, my drive will all the time change these values. And I say, okay, I can also create transport surface for my next conveyor and the same stuff. Okay. So now when I play it, I can see my box going down. I can click on it and view it in my runtime inspector. So I can see what my parallel speed and my parallel positions are. Okay. So the next bit now, we will look at some sensors. As we can see here in the drop-down menu, we have a lot of sensors. So collision sensors, just to identify or detect collisions. Some distance sensors that will tell you how far is your object from your sensor, position sensors, some limit switches if you want to define the hardware limits, etc. So let me just quickly define a collision sensor and let me create that as a collision sensor. Again, I can define different shapes. So if it's just a line like this one, I can just select a line, but right now I keep it as a box. In the detection type, I have 3 options, system, user, and both. System is when the actual object collides with the sensor it activates. User is during runtime, the user or I can activate the sensor. And both is when it's either user activated or system activated. So when I say okay, and if I play it, I can right click on it. I can add it to my inspector again, just to see when it's triggered. And when I play, it's false right now and it goes true when I activate here, but also when the box goes and collides it, it will again be activated. Okay, so this is our basic creating some sensors very quickly. The next thing we want to see is the material flow. Obviously, right now we see one object, one box coming down the conveyor, but in reality there will be loads of boxes coming down the conveyor doing some sequence, and then at the end we want that to disappear. They could possibly be falling down there, but they would continue falling down forever, and that makes my simulation really slow. So I want to create some sort of a sink, and my object, when it goes to the sink, it just disappears from there. To do that, I have to create an object source first. So I go and select object source. I select that as my object source. It could be time-based or once per activation. So activation is again user interference during simulation. I can click from my mouse, or I can have a tag coming from PLC that's saying create a new object now, create a new part now, create a new part now. Or it could just be time-based and I can say create a part every 2 seconds. Okay. Similarly, I can create an object sink. So I can select the sensor that I've defined at the end, and I can define the source. So right now I only have one source, but you could have multiple sources for different parts, and you could say, how do you want this thing to react to which source? So right now it's any, and okay. Now when I play it, we can see the objects coming down every 2 seconds, going down the conveyor, and when they come in contact with the sensor, they just disappear from there. So this is our material flow defined now. Okay. We will now have a look at few joints, some basic joints. And you can find all the joints here. So hinge joints, sliding joints, cylindrical joints, some sorts of point on curve or path constraint, which are used for some complicated functionality. But you can also find some spring joints. You can find some braking constraints, some spring damper. And then we have loads of couplers. So we can have gears, we can have pulleys and belts, rack and pinion, and we can have mechanical and electronic cam, which we will be going in detail in a bit. Okay, so how to create a hinge joint. Hinge joints, basically anything that's moving across one central axis, rotating around one central axis. So I create a hinge joint, I say attachment, let this be my attachment. I don't select any base because I believe that it's just fixed here in the 3D space at this point. So my axis vector would be this. It's rotating around that x-axis, and this is my anchor point. Once I do that and I say okay and I play, you can see that this is now moving. There's no control to this. That's why it just falls in gravity, and after some time it just comes down to stop. This doesn't move at all because, as I said earlier, you can see this in the 3D space. But in terms of MCD, in MCD world, this does not exist. I have not given any physics to it. So we will create a hinge joint for that as well. This time, this is my attachment and this is my base. My axis vector again is this direction, as we can see, and my anchor point would be here. And I say, okay. So once I do that, now we can see it's moving like that. And this is how when we want to create some robotic arms, hinge joints are the joints that are mainly used. Okay. A few more joints then. Let's have a look at sliding joints. So sliding joint is an object moving, sliding across any body or any part. So I can select an attachment again. Now again, base, I could either create that, select that, or I could just leave it as it is. When I don't select a base, it binds my attachment to just move in the direction of the axis. So if I select this as my axis movement, it's the movement of my part is restricted only in this direction. I okay, and when I play it, you see that I can move it across like that. Yeah, so that's my sliding joint created, but there is no control to that. I can create a hinge joint like I created earlier. So if I want to create, this is my attachment again, this is my axis vector, this is my anchor point, and okay. If I play it now, you can see that I can move it around, but it doesn't move forward. And if we wanted something to rotate and also move, then we have something called cylindrical joint. So for cylindrical joint, I have an attachment here. Again, same stuff, axis vector, anchor points, and okay. When I do that, you can see that it also moves and it also rotates. And the last thing to show here would be a screw joint. So screw joint is when I define a pitch. So every rotation it moves that much of the length. How it appears here, these screws or these pitches that don't actually exist in the MCD world. So we can change the appearance here, but that would not affect the movement of my component. The only thing that affects the movement is what I define here as the pitch. So again, my attachments, my axis vector, my anchor point, and let's say pitch of 10 mm, and I say okay. So when I play this and move this is going to move like that, like a screw. So we had a look at a few joints now. To control the movement of these joints, we need some sort of control. So we have a few controls here, like position controls, speed controls. We also have some force and torque control. So let's have a look at the speed control and select the object. Now, because this is only a hinge joint, I can only specify speed in degrees per second, and I can say okay. I can create another speed control. I can select the object. In this, it gives me an option to select whether it's linear or angular because I have two movements. So I can say linear 100 millimeter per second, and I can create again, and I can say angular, say 100 degrees per second. And I say, okay. So when I play this now, you can see this moving. And in the physics navigator, we should be able to see all of these. So if I just click on them and I go here, you would be able to see the changing positions. So that's how very quickly you would start creating some joints, applying some speed control. You can also apply some position control, in which instead of specifying the speed, you would just specify what's the right position. Okay, so then let's go back to our initial machine. Here we have created already the material flow. Now we probably want to create some sort of operation to be able to see if it can follow some sort of sequence. But before that, I want to show you how we can add some components if we wanted to. So I can go in my assemblies here. I can go and say add component. In the add components, I can just direct it to wherever my component is, the directory basically, and I can select the components and I say okay. So once I do that, I can snap it. I can decide where I want to keep that, and I want my component here. So that's where it's selected. I can also move it around if I wanted, if I was not happy with the position. So let's say this is the position which is the best for me, and I say okay. So I can see now very quickly I have introduced a new component to my machine. I can also copy paste it and put it here as well, but that's not the need. We're just doing some concepts here. So if I now go in my assembly navigator, you can see that I have a component that exists here. If I wanted to work on a sub-assembly level, I can right click on it. I can say open in window. What it does is it just opens that file for me. And I can also start giving some physics on the sub-assembly level, which is replicated on the top assembly. And if I copy paste these objects so many times, all of that physics would appear so many times. Okay, so let's create a hinge joint very quickly. Sorry, a sliding joint. So my attachment is this. My axis vector would be this, and I say okay. So when I play this, you would see it falls down. It fell down because if you notice the Z direction is there, so the gravity works in the negative Z direction. So it falls down like that. We can now apply some position control to this. So we have a position control. I select my joint and I can say destination 0 and speed 1500, and I can write to this destination when I start writing my operations. When I say okay, now it doesn't move because it's now controlled by my position control. I can go back to my top assembly, and when I go back to my top assembly, you can see now in Physics Navigator, we have extra rigid body and a sliding joint and a position control that is a part of that owner component. And if I were to copy paste it, it will just replicate. And I can play this. I can add my position control to my inspector and I can change the position to say 1000. And when I do that, you can see that it coming out. Okay, so we probably now want to write some sort of an operation, and we can write operations by clicking on this. We can select what we want to write. So what is the physics object that is being affected by my operation? And this would be my sliding joint of the pusher. So I want to change the position of my pusher to 1500. And is there any condition related to it? So I can say yes. The condition is when my collision sensor is activated. And I say okay. But I can also write another operation which says, again, for my same position control, and it says my position goes to 0 if my collision sensor is not activated. Okay. So once I do that, we can go in operations, and I can see I have two operations written here now. They are event-based operation, which means they're followed by an event. So a collision sensor is triggered, but we can also have time-based operations or linked operations. So linked means one follows another operation, and time-based if it happens at certain time of the simulation. You can double-click on it. If you wanted to change something, you can edit it here if you want. And cancel. So let's play this. And if I activate my sensor, you see it comes up. And it will also come out when any of the boxes activates the sensor as well. Okay, let's stop it. So the next thing we can have a look at is writing some background expressions very quickly. So if I go back and if I delete these operations, so these operations don't exist now. And here you can see there's something called runtime expressions. So this is again the parameter to assign what are we trying to write to. And we can say we are trying to write to the position of my position control. What are my input parameters? So input parameter is my collision sensor. And whenever it's triggered, it should be writing something to it. So in my formula, I can just get some condition builder to create some basic condition for me, and I can start writing. So I can say if my collision sensor is true, then you go 1500, otherwise. So now I have written a background expression that runs during my simulation, and I can play again. And I can see when I click it, this works again. Okay, so this was just a very quick overview of what MCD looks like, how you can start getting started with it, how you can create some rigid bodies quickly, collision sensors, some joints, some position and speed control, and some operations and background expressions. Ideally, we would have to not write the operations because that sequencing is done in your automation side, and we can connect all of the sequences to MCD directly. So all of these values of speed, of position, they should be coming from your automation. But if you wanted to test something really quick, we can obviously write it in MCD as well. Right. So this was our overview. Moving on to the next thing on our agenda would be inverse kinematics. Okay. So it allows us, inverse kinematics is in functionality now, which allows us to quickly create some paths, and I can create some points, move my robot to those points and create whatever path I want to. So as we can see on the left-hand side, we have 6 rigid bodies because it's a 6-axis robot and 6 hinge joints. If I play it now, it's just falls down, nothing happens because I don't have any controlling it. And I can apply something called inverse kinematics now. So I click on inverse kinematics. I can have offline or online simulation. So offline is when I define the points not during simulation, and online I can keep changing the points, so that could be written. That's where the virtual commissioning bit comes in. When we create an online inverse kinematics from my automation side, from my controller, I can keep writing to the positions of the robot, do some teaching using, say, my HMI, and save those positions. Right now I will do some offline kinematics. I will select the objects and the points. So this is my initial orientation, and then we can add some poses. So let's add the first pose, and we can select here. So that should be my first pose. Orientation needs to be changed sometimes, but when we play around with this, we know what's the right orientation to be. And I say, okay. When I do this and play, my robot goes and it just follows this trajectory. So I can also have a tracer that tells me how it's moving. When I created inverse kinematic, you can see that a few position controls are automatically created for me. And also some operations are written. So it's basically the operations that are controlling the movement of all the 6 joints, moving all at the same time. I can go back and I can add more poses. So I can add a second pose, let's say here, and let's change the orientation again. And okay. Yes. So when I do that and I play, it will go there first and then there very nicely. And now we can see the trajectory. And now you can see there are 2 sets of operations that are being written. Once they are written, I can manipulate them. I can move them around. So if I wanted to give some time in between, I can do that. And I can play again. So it goes there, stops there for some time, and then goes back there. and I can get all the actual values of the XYZ coordinate of my point at any point during the simulation. Right, so I can create another pose very quickly just to show you. Goes like that, goes like that, 90, and I say okay. Yes, so it goes there, and goes back very nicely. And now we can start having interactions with different robots or different parts of the machines if I wanted. Now this is obviously one robot that we were working on. What if I wanted to replicate, I wanted to reuse all the work that I've done, all the parts that I've created? I could do that. So if I go in my assembly navigator, I can bring in another robot here. You can see there's a different robot with different arm lengths and everything. And I will close my existing part. So let's just delete this. Okay. So now we can see that I have everything related to KUKA, all the hinge joints and the rigid bodies. If I go in inverse kinematics, everything that I have created earlier, I can select the objects. I can specify the points. And that's it. And I say, okay. So it again created some position control for me. And when I play, oops, sorry. It's a different pose it created. But I can go back and I can check what's the different poses it's creating for me now. So it's very easy to replicate all the work that we've done. And we can work between different robots. We can have any different lengths. We can also bring stuff from library and keep changing those stuff and work with them. Okay, so that was the offline programming. Go back and bring my ABB back on and close that part. Okay. Okay, so now I have my ABB robot again. What I see here now is a point, and this point is moving around this specified path. How it's doing that? This is a joint, as I said earlier, called point on curve joint. So you can define a curve, you can have a point on that curve, and it will follow you. So it's really used when you have some non-linear movements. So you can say when I play this, at any point of time during simulation, my rigid body is changing the values, the XYZ coordinate values, as you see here. And what I want to do is I want my robot to follow these. So again, I will go in inverse kinematics. I will go online, select the objects, specify the point again. Okay, and that is it. So when I do that, it creates just inverse kinematics and tracer for me. Nothing happens right now because I have not mapped the value of this point to the inverse kinematic bits. So to do that, we have something called signal adapter. Now, signal adapter is not just for that. Signal adapter is a functionality that allows you to link different parameters to some other parameters or some signals, some Boolean or analog signals. We can also use this to connect to your automation PLC tags, if you like. So you can create some signals here. You can bring some parameters from your already existing physics in your signal adapter, and you can start creating some formula, just like we did in background expressions. So I will select the rigid body here, and I'm interested in the center of mass for X, center of mass Y, and center of mass Z, because I'm interested in the values of the vector values of these 3 points. So I can simply call it X, call it Y, and Z. Okay. These values have to be written to my inverse kinematics. So I select inverse kinematics, position X, position Y, and position Z. Okay, so this will be, let's call it IKX, I, and IK. And all I have to do is click on these 3. When I do that, I can assign to these. And what do I want to assign? I want to assign to ikx the value of x. I want to assign to iky the value of y. And I want to assign to ikz the value of z. And I say, okay. And when I play this, you can see that my robot is now following the exact movement of that point. I can obviously get rid of my curve if I wanted, if I didn't want to see it, and I will just see my robot moving like that. Okay, so this is the online teaching for the robot, and we don't really have to have this rigid body or this point. Ideally, these points should be coming from my controller directly. There's some other stuff that I wanted to show you. So there's something called joint jogger. When you have created some joints and you want to just make sure they're moving the way you want to, you can use this functionality. And you can also save them in some specific form. So if you wanted your robot to have the default state of this, you can have that and you can apply to it. So it will be on that default state. Okay, so that was our second section completed for inverse kinematics. And now we will have a look at our last bit, which is the cam profile generations. So we come back to how we can generate some cam profile very quickly using the operations. We know now how to write operations. So we will be using that functionality to get some values out of, get some data out of my operations here. What I have here, few rigid bodies, as we can see, a hinge joint here, a hinge joint here, a hinge joint here, and a sliding joint for my pushing pole. This right now, we can ignore this. It does not exist. We will see why I need it later. I have a position control that is controlling the movement of my pushing pole. So in the real world, I would know that I want my pushing pole to move in this direction over a span of time, say from 0 to whatever seconds. And this should be the movement. This should be the millimeter movement of my pushing pole. But I don't know how this should be reacting. What would be the degree what would be the degree movement of my cam with respect to that? And I want to find that out to basically write my cam profile. So I have an operation written here, which is basically moving my, controlling the position control of my arm, and it's moving it forward and backwards. So when I play it, you can see it goes like that. And now I want to mimic this movement. I want to create a cam profile for this. So then I can actually import it in TIA portal and use my TIA portal or my controller to actually control the cam. Right. So first thing we do is we add in my runtime inspector the value, my hinge joint. So when I add to my runtime inspector my hinge joint, the thing I'm interested in is the angle. So how does the angle change when my arm is moving? I can click on graph, I can click on export. This simply means it creates a graph for me, and this allows me to export the values in CSV format. So I go in graph, and when I play, I can see a graph being generated for my cam plate hinge joint. So I can stop it and I can go back to the inspector and I can export from down here. So just select a file name, we call it data2, and I say, okay, export. So the data is exported successfully. So let's create a cam profile now. A cam profile. My master is time right now, so I don't have this as a slave and any other master. My master is time and my slave is the rotary position, my rotary movement of the cam, and I can import the file that I just exported. So when I import it, you would see that it's quickly created this cam profile for me, all the 5-degree polynomial equations of all the points and transfers of segments and everything. So I can just say, okay, that's created that for me. I can create an electronic cam now. So again, my master is time, my slave axis is my hinge joint. Before that, I need to have a position control because my slave axis is always a control. So time, my slave axis is my control for my hinge joint here. That's my profile. And okay. So if I deactivate the position control for my pole and if I deactivate these two, so we don't want the operations to be controlling it. If I did not have my electronic cam, nothing will happen. If I have my electronic cam, it's controlled by my cam now. So it's exactly the same movement being followed here. But what I want to do now is I want to create a cam profile so that this is my slave and that is my master, and this is being controlled by the movement of that. It's a similarly, we can, when we run it, I can create graph for how my hinge joint changes with the movements of my sliding joint position of this. So millimeter versus degrees, linear versus rotary. And once I've done that, I can again export it, and I have already done that before, so I can show you how that looks like. So this was my data from when I just exported my hinge joint angle, so you can see with change in time how my angles are changing. And I also have data for my hinge joint against my sliding joint position. So when my hinge joint changes like that, my sliding joint positions are changing like that. Okay. Let's just don't save it. And if I create another cam profile then, this time my master is rotary, my slave is my linear position. I can import again. And when I import it, you can see that on the x-axis is my master 0 to 360 degrees, and on my y-axis is my slave 0 to 200 millimeters. And okay, so I've created two profiles now. I can create another cam, electronic cam. And this time my master is not time but an axis, which is the master axis, and my slave is this. My motion profile is the one I created just now. And I can say, okay, once I do this and I play, it follows my cam profile. So this was all done in the MCD, very quickly creating the profiles and making sure that now the profiles are correct. But once I've done that, I can go back to my cam profile and I'm happy with it. I can export it in Scout format, export to Scout, and that can be directly imported in TIA portal. So then I don't have to have these cams here at all. I can delete all of that, and now everything is controlled by my automation side. And that I will show you in a video that I have with me. Just give me a sec, I will play it. Here we go. So this is what we just saw right now. I have a master axis here and I have two slave axes. So one is a screw joint, one is a sliding joint. This one will work as a mechanical cam. This will work as an electronic cam. So when I play it, you can see what's the movement I like. Again, using the operations, I can quickly create my cam profiles. And so the cam profile is generated using operations with an MCD. And once you do that, you can export them. But if it's a mechanical cam, you can actually create an actual cam as well. So once I have imported the motion profile, I can say create an actual cam. And it creates the actual cam for me, which can then be exported as a DXF file, and you can start actually producing your physical cams. But we are actually interested in electronic cam. So what we can do is we can export, as I said earlier, the profile. It is a CSV format again. So it's exported and I can say, okay. So my profile is exported now. What we see now are two machines which are exactly the same, but this is controlled by MCD. So we have the electronic cam with an MCD, and this is controlled by PLC. So no cam exists within TIA for this. So nothing happens right now because we have not imported the cam profiles in PLC. They do not exist in the software yet. So we quickly go in TIA portal. I go in my technology objects. I can create my cam technology object. Add a new object, a technology object cam, okay, and I can import my profile, the one that I just created. So once I do that, it quickly imports those profiles for me, and I can download them to whatever program I have. I can link it to my program, and it's downloaded in my PLC Sim Advanced instance, and I can use HMI now to start controlling it. So once now I play it, I have some set point for my master, and we can see that these two are reacting to the master set points. It's not working correctly, so we can change the speed possibly, make it match the master, the speed here, and we can see that it works with, say, a certain speed. So this is again now commissioning and making sure the profile is correct and is working the way it's supposed to work. So these are the 3 topics that we covered today. It was a bit of a deep dive,